Hello, students, and welcome. Have you ever looked at a light bulb and wondered what that watt rating on it really means? Or maybe you've heard your parents discussing the electricity bill and wondered how it's actually calculated. Well, today, we are going to explore the very important topic of electric power. So here's our plan for today. We'll start with the very basics. What exactly is electric power? Then, we'll look at the different formulas we can use to calculate it. After that, we'll see how all of this applies to your real-life electricity bill. We'll also explore how power turns into heat and light, and look at an important safety device called the fuse. And finally, we'll practice everything by solving some problems. Okay, so let's think about all the electrical appliances we use at home. You know, the fan, the television, your mobile phone charger. You already know that they all consume electrical energy to work. But have you ever thought about whether they all use energy at the same speed? An air conditioner, for example, uses up energy much faster than a tiny night bulb. So the question is, how do we measure this rate, the speed at which they use energy? Well, that's exactly what electric power is. It's simply the rate at which electric energy is used up in a circuit. You can think of it as how fast the energy is being consumed. The most basic formula, the one you should always remember, is P equals V into I. Here, P is for power, V is for the potential difference, or voltage, and I is for the electric current. Now, how do we measure power? The standard unit is the watt, named after the famous inventor James Watt. So 1 watt of power is used when 1 ampere of current flows across a potential difference of 1 volt. But, 1 watt is a very small amount of power. For our bigger appliances at home, like a refrigerator or a water heater, we use a much bigger, more practical unit called the kilowatt. And it's simple. 1 kilowatt is just equal to 1,000 watts. So we have our main formula, P equals V into I. This is our starting point. But what happens in a numerical problem where you are given the current and resistance, but not the voltage? Or maybe you have the voltage and resistance, but not the current? Well, this is where our old friend Ohm's law comes to help us. We can use it to create 2 more very useful forms of the power formula. Let's see how this works. It's a very simple substitution. We start with P equals V into I. Now, from Ohm's law, we know that V is equal to I into R. So let's replace V in our power formula. We get P equals IR into I, which gives us P equals I squared R. Simple, isn't it? Now, let's start again with P equals V into I. This time, let's substitute for I. We know I is equal to V by R. So P becomes V into V by R. And that gives us our third formula, P equals V squared by R. So now we have 3 different tools to solve our problems. So which formula should you use? Now this is a very important tip for your exams, so listen carefully. Remember, in a series circuit, the current I is the same through all the components. So the formula, P equals I squared R, is the most useful one. But in a parallel circuit, like the wiring in our homes, it's the voltage V that stays the same across everything. In that case, using P equals V squared by R will make solving the problem much easier. All right, let's move on to something very practical, something your parents deal with every month. Let's try to understand the electricity bill that comes to your home. Now, this is a very common point of confusion, so it is important to understand the difference between power and energy. Power is the rate of using energy. It's like the speed of a car in kilometers per hour. Energy, on the other hand, is the total amount that is consumed over a period of time. It's like the total distance the car has traveled. The electricity company bills you for the total energy you use, not for the power of your appliances. Have you ever heard your parents say, "We used 100 units of electricity this month"? Well, when they say unit, they're actually talking about the kilowatt hour. This is the commercial unit of electrical energy. So what is 1 kilowatt hour? It's simply the amount of energy you use when an appliance with a power of 1,000 watts runs for 1 full hour. Now here's a very interesting misconception to clear up. Many people think that we are paying for the electrons that the electricity company sends to our house. But this is completely wrong. The electrons just move through the wires of our appliances and go back. We are not consuming them. What we are actually paying for is the energy that is needed to push those electrons through the circuit to make our appliances work. I'm sure all of you have noticed this. After you charge your mobile phone for a while, the charger feels warm, right? Or an electric iron gets so hot that it can press clothes. This happens because of something called the heating effect of current. Let's discuss this now. This heating effect is explained by Joule's law of heating, The formula is H equals I squared RT. This formula tells us that the amount of heat produced, H, depends on three things. It's directly proportional to the square of the current, I. This means if you double the current, the heat becomes 4 times greater. It's also proportional to the resistance, R, and the time, T, for which the current flows. So this raises a question. If current produces heat in every wire, why does the wire inside a toaster or a room heater glow red hot, but the copper wires in our walls don't? Well, it's all about the material. Heating devices use special alloys, like nichrome. Why? Because these alloys have very high resistivity, which means they produce a lot of heat. They also have a very high melting point, so they can get extremely hot without melting. And they don't burn or oxidize easily, even at those high temperatures. Now just look at this table. Let's compare the numbers. You can see the resistivity of copper, which is a good conductor, is very, very small. But look at nichrome. Its resistivity is much, much higher. This is exactly why nichrome is used to make heating elements. It's designed to resist the flow of current and produce a lot of heat. It's the same idea for the filament inside an old-fashioned electric bulb. For the bulb to give us light, that tiny wire inside has to get incredibly hot. It has to glow white hot. That's why it is made of a special metal called tungsten. Tungsten has an extremely high melting point, almost 3,400 degrees Celsius. This allows it to glow brightly without melting away. So we have seen that the heating effect can be useful for things like toasters and bulbs, but too much heat can also be very dangerous and can damage our appliances. And that's why we need a very important safety device that actually uses the same heating effect, the electric fuse. So how does a fuse work? It's actually a very clever and simple idea. A fuse is basically just a short piece of wire made from a material with a very low melting point. It is always connected in series with the appliance it needs to protect. Now, if for some reason the current in the circuit becomes too high, the fuse wire heats up very quickly, melts, and breaks the circuit. The flow of current stops and your expensive appliance is saved from damage. So the fuse is like a little soldier that sacrifices itself to protect the rest of the circuit. Okay, we have discussed a lot of theory. But as you know, the best way to really understand these concepts and prepare for your exams is to solve some numerical problems. So get your pens and notebooks ready. Let's practice. Here is our first problem. Let's read it very carefully together. An electric bulb is connected to a 220-volt generator. The current is 0.50 amps. The question asks, what is the power of the bulb? So the first step is always to write down the information that is given to us. We have V equals 220 volts, and I equals 0.50 amps. We need to find P. Now we need to find power, P. We know the voltage, V, and we know the current, I. So which formula connects these three things? Yes, it's the very first one we learned. P equals V into I. Now we just have to substitute the values. P equals 220 multiplied by 0.50, and the calculation gives us 110. So the power of the bulb is 110 watts. And please, always remember to write the correct unit in your final answer. Okay, let's look at problem number 2. Now read this one carefully. An electric refrigerator is rated 400 watts. It operates for 8 hours every day. We need to find the cost to run it for 30 days if the rate is 3 rupees per kilowatt hour. So you see, this question is different. It's not asking for power, it is asking for the total cost. This is an energy calculation. This is a multi-step problem, so let's solve it one step at a time. First, we need to find the total energy consumed in the month. Energy is power multiplied by time. So 400 watts multiplied by 8 hours per day multiplied by 30 days. This gives us 96,000 watt-hours. Now, step 2. Remember, the cost is given per kilowatt hour, so we must convert our answer into kilowatt hours. We do this by dividing by 1,000. So 96,000 divided by 1,000 gives us 96 kilowatt hours. Now for the final step, calculating the cost. We multiply the total energy, which is 96 kilowatt hours, by the cost per unit, which is 3 rupees. And that gives us our final answer, 288 rupees. So the cost of operating this refrigerator for 1 month is 288 rupees. You see? Understanding these formulas is not just for passing exams. It helps you understand the world around you. From calculating your electricity bill to understanding why a toaster works, you now have the tools to understand electric power. Make sure to revise these concepts well.